is equal to 50. This is positive. Oh, wait on. I don't know what's wrong with me today. The second derivative of that is negative 2. This is negative, therefore concave down. So in other words, like that rather than like that. Therefore local minimum. So local maximum. Okay. And so that is another way of proving that you have a local maximum. One way is to draw it in 3 parts. Another way is to use the second derivative to show that it must be that rather than that. Okay? Now, here's another example. This is just straight from the book. We've got, we have to make a rectangular cuboid tank. It's got a base but no top, and we're given 54 square meters of metal to play with. And we've got to make this thing have as much capacity as possible. Okay? So, just a quick little diagram. Here's the box. Why don't we call... Oh, sorry, I forgot to say it's going to have a square end. Okay? So therefore we can use x for that and x for that. And we just have to use y for that. Reluctantly using a second letter, which I only do when I have to. Now, if we want to make this have as much capacity as possible, we're obviously interested in volumes. There's the formula. Now we've got to try and state a factor with that. Now, that is how much area, that's how much metal we've got to play with, so that must be the surface area of this guy. So 54 is x squared plus the front plus the back plus the bottom. So in other words, 50 is equal to 2x squared plus 3xy. Now we've got to get something that's ready for calculus. Okay, so how could I do that? Well, why don't I get y by itself here? So 54 54 equals 3xy equals 54 minus 2x squared. So y equals 54 minus 2x squared over 3x. Now, volume therefore equals x squared, not y anymore, but rather 54 minus 2x squared over 3x. Which I'm going to expand the bracket, 54x squared minus 2x to the power of 4 all over 3x. I'm going to unadd that fraction. Or unsubtract that fraction. I'm now going to cancel this. And that's now ready for calculus. And so here's my multiple choice box. And now we're good to go. Now I want to find out where that's flat, because when it's flat will be the top of a little crest. Okay, so flat means that I put a 0 there. Let's get some more paper. So put a 0 there. solve this. Oh, I'm having a shocker. Oh, I left out a 2 there. I'm sorry. So x equals 3 or negative 3, so we're going to cut the negative 3 because you can't have a negative length. Okay, that tells me that it's a 3 underneath where it's the highest, but now we have to do the proof. Oh, I can actually now find out how high it is when it's at its highest. Put a 3 back in there, so that's 54 minus 2 times 27 over 3, which is 54 minus 18, which is 36. Okay, so the highest volume it gets is 36, and it gets it when x equals 3. But how do we get full marks? Okay, we get full marks by proving that we found a maximum. Okay, so 2 ways. I'll do them both. There's a table and then a second derivative. Okay, let's do the second derivative first. Just continue differentiating this. You get negative 4x. If x equals 3, the second derivative is equal to negative 12. This is negative, therefore concave down, therefore local max. Okay, or you can also use a table and draw a little broken picture. Our magical value was 3. I'm going to use 2.5 and 3.5 just to stay nice and close. So stick 3 and you obviously get 0. Stick 2.5 in. 2.5 squared is 6.25. 2 times 6.25 is 12.5, so I think that's 5.5. So it's rising, then it's flat. Put 3.5 in. 3.5 squared times 2. 18 take away 24.5 was negative 6.5. So there's the fall. Therefore, local max. Now either of those is fine. Both of them establish that you really did find the highest point of a curve. Now, whenever you've done this, make sure you've answered the question. They'll ask you what's the greatest volume it can be, 36. They'll ask you find the value of x that gives the volume, it's 3. They'll often say, often they won't even say prove that you found a genuine maximum. You have to do it even though they don't ask for it.